We start by seeking a single vector B1 in d-dimensional space that maximizes the variance of the projected data. That is, we aim to maximize the variance of the first coordinate, z1 of z in m-dimensional space, so that v1 equals the variance of z1, which is 1 over n times the sum of z1n squared, is maximized, where we exploited the independent and identically distributed assumption of the data and defined z1n as the first coordinate of the low-dimensional representation zn in m-dimensional space of xn in d-dimensional space. Note that the first component of zn is given by z1n, which is equal to b1 transpose xn. That is, it's the coordinate of the orthogonal projection of xn into the one-dimensional subspace spanned by b1. Substituting from the previous slide, we get that v1 is equal to 1 over n times the sum of the z1n squared terms, which in turn is equal to 1 over n times the sum of b1 transpose xn squared. Using the fact that the dot product of two vectors is symmetric with respect to its argument, we get that this is equal to 1 over n times the sum of b1 transpose xn times xn transpose b1. We can then take out the b1 terms and get b1 transpose times 1 over n times the sum of xn transpose b1, where that bracketed term is equal to s. And so we get b1 transpose times s times b1. Now notice that arbitrarily increasing the magnitude of the vector b1 increases v1. That is, a vector b1 that's 2 times longer will result in a v1 that's potentially 4 times longer. Therefore, we're going to restrict all solutions to where the norm of b1 squared is equal to 1, which results in a constrained optimization problem in which we seek the direction along which the data varies most. With the restriction of the solution space to unit vectors, the vector b1 that points in the direction of maximum variance can be found by the constrained optimization problem to maximize over all b1s b1 transpose sb1 subject to the norm of b1 squared equals 1. From here, we look at the Lagrangian. L of b1 and lambda equals b1 transpose sb1 plus lambda 1 minus b1 transpose b1. We can use this to solve a constrained optimization problem. The partial derivatives of L with respect to b1 and lambda 1 are dl db1 equals 2b1 transpose s minus 2 lambda 1 b1 transpose, and dl d lambda 1 is 1 minus b1 transpose b1. Setting both partial derivatives equal to 0 and solving gives us the relationship sb1 equals lambda 1 b1 and b1 transpose b1 equals 1. By comparing what we have with the definition of the eigenvalue decomposition, we can see that b1 is an eigenvector of the data covariance matrix S, and the Lagrange multiplier lambda 1 plays the role of the corresponding eigenvalue. This eigenvector property allows us to rewrite our variance objective as v1 equals b1 transpose sb1, which is equal to lambda 1 b1 transpose b1, which is equal to lambda 1. That is, the variance of the data projected into one-dimensional subspace equals the eigenvalue that is associated with the basis vector b1 that spans this subspace. Therefore, to maximize the variance of the low-dimensional code, we choose the basis vector associated with the largest eigenvalue of the data covariance matrix. This eigenvalue is called the first principal component. We can determine the effect or contribution of the principal component B1 in the original data space by mapping the coordinate Z1n back into the data space, which gives us the projected data point xn tilde equals B1 Z1n, which is B1 transpose xn in Rd. Now, although xn tilde is a d-dimensional vector, it only requires a single coordinate, Z1n, to represent it with respect to the basis vector B1 in Rd. In the next video, we'll discuss m-dimensional subspace with maximum variance.